Welcome back to the Sun, Wind, and Light Tools demo video series. This video takes you through the process of quickly estimating heat loss. I'm Mark DeKay and I'll be giving you this tour. As you know, if you saw the first video, the SWL Tools spreadsheets support the use of the methods and tools in Sun, Wind, and Light 3rd edition. We've said that the 3rd edition is focused on net zero and plus energy buildings. This energy balance in a building is a balance between the building's energy use and its energy production. So first we'll spend a good bit of time understanding and reducing the energy loads so that the green energy supply system, such as PVs, will be as small as possible. Right now I'm going to go over to the Quick Heat Loss at the bottom of the page. Click on the Quick Heat Loss tab and we'll be looking at this sheet. And this video will take you through all of the things that you need to know about this worksheet. First, we'll find the envelope conservation criteria for our climate in Knoxville. So I'm going to go up here to the envelope conservation criteria and know that we want to choose an envelope conservation criteria that's based on the severity of the heating season. And to measure this, we use heating degree days. That's where listed right here as HDD 65 Fahrenheit. Degree days are available from many sources, including ASHRAE and many online sites. But I'll go back to the engineering weather data that we used in the past. And you'll find the degree days in your file on page 13. I'm looking at page 13 now, and there's a graph here that shows the degree days for the heating season and for cooling, and these are typically measured to a base temperature of 65 degrees. So you may remember that degree days are determined by, for a given day, the difference in degrees between the average outside temperature and some base temperature, and it's typically 65, but it could be some other base temperature. But in the ASHRAE file here, it's 65 degrees. And if you add up these differences between the outdoor average and the base for every day of the year, then you get a total annual heating degree days. So you can see from this graph that January is the coldest month with the most heating degree days, and July is the hottest month with the most cooling degree days. And some months have both heating and cooling degree days. For Knoxville, it's clear that there's more red than blue, and so heating is a more significant issue than cooling. The table down below shows the total annual heating degree days for Knoxville are equal to 3946. Next, we'll look at the analysis technique in Sun, Wind, and Light called total heat losses in the 3rd edition. So I'm going to close this and pull up my SWL electronic pages, and I'm going to go to page E354. So you'll notice over here on the right hand side there's a footer. This is in section A27 or analysis technique, A for analysis. This is the analysis technique called total heat loss and total heat gain. We're on page E354. So let's look at the table titled Building Conservation Criteria based on total heat loss rate. That's at the bottom of the page. And for our degree days of 3946, that would fall roughly in the middle of the 3,000 to 5,000 annual degree day range. That's here in this row. So our annual maximum heat loss rate would be 7 BTUs per degree day per square foot of floor area for a conventional non-solar building, and 5.6 BTUs per degree day per square foot for passive solar buildings. Now the difference between these two in the heat loss rates is that the solar building does not include loss through the solar wall. The solar wall has a high proportion of solar aperture, and it's considered a net energy gainer. Now let's go back to the quick heat loss page, and with those in mind I'm going to put in my degree days here, 3946, and my conventional building is a 7, and my passive solar building is a 5.6. So now what we've done is set up the heat loss criteria. Now we'll look at the skin heat loss and the ventilation and infiltration loss. We'll add those up together and see if it is less than the criteria for conservation. So in the next section, we'll look at the conductive heat loss through the skin elements. Remember that conductive heat loss through a wall or a roof is proportional to the U value of the assembly and the area of the material. One way to remember that is just the simple formula Q, or heat loss, equals UA delta T. That is the U, or the U factor for the assembly, times the area of that portion of the building that you're looking at, whether it's a wall or a roof, times the difference in temperature between inside and outside. But in this case, we're doing it on a per degree basis, so we'll just look at the UA. I've already input for this little building that we're looking at the gross wall areas. So we're breaking those wall areas down into north, west, and east, and we're leaving out the south wall. We also have a roof and a floor. And then we also have the non-south glazing areas. So remember, again, because we're looking at a solar building, and I'm going to assume that you're all going to be doing solar buildings here, this quick heat loss method is set up to ignore the south glazing in terms of its heat loss. We'll account for that later when we look at the solar savings fraction. So the building elements can also be renamed, like for instance, if you didn't have a north wall, you had a northeast wall, you could edit that. You could even spell it correctly, northeast, and so forth. These labels are just for your own reference. So you can use any kind of orientation, whichever orientation the building actually has. There's two types of inputs in this section for skin R values. There are the recommended R values for your climate and the R values that you're actually using. And both of those are down here in the lower portion under skin heat loss. To find the recommended R values, we'll go over to the skin thickness strategy in Sun, Wind, and Light. So I'll pull up my Sun, Wind, and Light electronic again. And this is on page E196. So I already looked that up. So this is the beginning of strategy number 74 for skin thickness. So let's take a look at this table, the first table in the strategy, called Low-Rise Residential Recommended Insulation, and this is in IP units. Note that the first thing that we need to know is what the climate zone is for the project that we're looking at. So in order to determine that, we'll have to look at the climate zone map. I'll go up here and go over to page E366, which is in the appendix at the end of SWL Electronic. It's also in the printed book in the section on navigating by climate. So here's Knoxville. Knoxville is in zone 4. That's a mixed climate, meaning that it has both heating and cooling needs, and it's on the moist or humid side of the country. So that would be climate zone 4A if you look it up on the associated table. So now let's go back to page E196 and we'll look at zone 4. So for zone 4, we can find the R values for the roofs, walls, floors, and foundations. Now these are recommended cost-effective R values. For Knoxville, the recommendations are for an attic R30 to R60, with R60 being for a high-performance building. On the other hand, if the roofing system is more of a cathedral or a compact roof where there's not room to pile up insulation on top of the joists, then the recommendation is for an R22 to an R38 with an R45 for a really high performance building. For wood frame walls, R15 to R21 with R25 for the high performance building. For mass walls, R16. For a wood frame floor, R25, or for a high performance wood frame, R30. Now let's input those values into our quick heat loss spreadsheet. So for the walls, we have an R15 to 25. For the roof, 30 to 60. And for the floor, a 25 to 30. Those are our recommendations. Now we need to enter what we're going to choose. Where are we going to be in that range, or shall we be above it? For the walls, I'm going to go on the high performance end and say an R25. For the roof, I'm going to go higher than the 30, but not as high as the 60, because I think some of my roofs are going to be sloped roofs without an attic. And if you remember, that range was 22 to 38 with 45 as the high performance. So I'm going to go with a 45 there. And then for the floors, I'm probably going to have some slab on grade or some mass floor in the end, but for now, before we get to looking at mass, I'm gonna try to go with the wood frame floor here, and we'll call that let's call that an R25, just because I think later we're going to have some different conditions. Okay, that's it for the assembly and the assembly R values. And next, what we'll look at is windows. For windows, the U-factor recommendations are given in the strategy Window and Glass Types Strategy 106. So I'm going to open that up now. Here's my Sun, Wind and Light Electronic. That starts on page 273. That's E273. And take a look at the table and the map titled Recommended Insulation Values for Windows in Passive Solar Heated Buildings. Knoxville is in East Tennessee, right over here in the border between zones 5 and 6 on the map. To be conservative, I'll use zone 5. Knoxville is a median priced area for fuel cost. Assuming that fuel costs will escalate significantly during the life of the building, I'll use the high fuel cost side of the table. Now, these recommendations are perhaps a little bit older, so if you're going to round one way or the other, round down on your U factor or up on your R value. For Knoxville, we find a recommended maximum U factor of 0.37. Let's input that into our spreadsheet. So I'll close this. We'll go back to the spreadsheet. The recommended at 0.37, and that will be the maximum U factor, so I'll go a little bit less than that to start off with in our calculation and put in 0.35. And you can see our skin heat flow rate in BTUs per hour per degree Fahrenheit per square foot of floor area is currently at 0.17. Now we need to estimate the heat loss from ventilation. Some people like to calculate either ventilation or infiltration, but more conservative engineers calculate both and then add them together. So we'll take a look at the ventilation and infiltration technique in Sun, Wind and Light. So I'll open my SWL electronic, and I'm going to go over to page 335. And page 335 is the ventilation and infiltration technique, technique A23. Now we'll look at the table, heat gain, loss from ventilation in commercial and multifamily buildings. So this table assumes mechanical fresh air ventilation. That's the distinction that we make between ventilation and infiltration. So ventilation is mechanically induced. We ventilate at a designed rate based on the number of people and the kind of occupancy that's happening in the building. Infiltration is being driven by wind pressure primarily. So we'll take a look here and we'll use the residential value from this table of 0.5. The units are BTUs per hour per degree Fahrenheit square foot. And it's okay that we're using multifamily here because it's based on how many people are present, so I'm assuming it's a small family. If you're designing for a large family, you could double it. So I'm going to use the average value, which represents the average occupancy condition. The maximum values would be used for peak occupancy. For instance, in the lecture room, if you were designing a school, if every seat in the lecture hall was occupied, that would be the maximum occupancy. But as we know, in most lecture halls or most classrooms, they're not occupied in every seat for every hour of the day. So we'll also need to account for infiltration. So I'll go down a couple of pages. and we'll look at the table heat gain loss from ventilation and infiltration in residential buildings. And you can see that the rate of heat loss is based on the construction tightness and whether or not heat recovery is used. If you were sizing a mechanical system for the worst case, for instance, you're trying to size the machine to take care of the coldest hour of the year, then you'd use the maximum here. But in most places the wind doesn't blow at 15 miles an hour all the time. So a more accurate estimate would be to use the average column. So the example we're working on will be a tight net zero building with heat recovery ventilation. So I'm going to use a value for infiltration of 0.02. Now let's input these into the spreadsheet. For ventilation, I've already entered 0.05, and you can see I have a 0.7 for my heat recovery efficiency. So I'm assuming that I'll use something like an air-to-air heat exchanger with about a 70% heat recovery efficiency. And then down in infiltration, I've already entered 0.02, and that's my infiltration heat loss rate. Well, that's it. That's all you need for a quick heat loss estimate. So if you scroll down, just at the top of the next page, you can see that the building's heat loss rate is given in BTUs per degree day per square foot, and then we can compare that to the heat loss criteria, which is shown in the same units. So our heat loss criteria is 5.6. The heat loss for the building, given the assumptions that we have made, is 4.8. Since 4.8 is less than 5.6, we meet the standard. We've met the criteria, and that's what we're shooting for. If it's larger than the criteria, then we would need to go back and change something in the inputs. You could either change the building form to reduce the areas, for instance, make a form that's less articulated and more streamlined so that it has less surface area. Or you could go back and change any of the other inputs, such as you might lower the window U factors, you might raise the skin R values, or you might add a heat exchanger if you don't already have one. And generally, once we have good insulation in the skin, windows are usually the culprit. So if you're following the guidelines for the recommended R values in the skin and you're still under, you might go back and look at windows. And the second thing to look at is ventilation or infiltration usually. So sometimes you might make some assumptions there that don't line up with the building, and that might be the problem. So note that this is a quick heat loss method. Later we'll expand the detail in the detailed heat loss worksheet to be able to account for other construction conditions such as below grade walls or slab on grade, doors, and more detailed ventilation calculations. Well, in the next video we'll learn how to use sun, wind, and light to estimate quickly the rate of heat gain that can be used to size passive cooling systems such as stack ventilation or evaporative cooling. Stay tuned.